We've seen how we can use the concepts we have learned in this chapter in the world of geometry. Now let's take things to the world of algebra and prove some complex statements. Here's the first one. If P and Q are the lengths of the perpendiculars from the origin to the lines x cos theta minus y sin theta equals to k cos 2 theta, this is our first line. And the second line is x secant theta plus y cosecant theta equals to k, then prove that p square plus 4q square equals to k square. So if you break this down, this is what we're given. The perpendicular distance from origin, which is 0, 0 to the line this is p, and the perpendicular distance from origin to this other line is q. So we're given the perpendicular distances p and q, and we need to prove this. P square plus 4q square equals to k square. How do we do this? Pause the video. Try this on your own. Okay, so here's a clue. The statement that we have to prove does not have theta, which means we need to figure out a way to eliminate theta. So let's do that. First, let's measure the distances. We can use the distance formula. Distance of a point from a line is given like this. Mod of ax1 plus by1 plus c divided by root of a square plus b square. This is when the point is x1, y1 and the line is ax plus by plus c equals to 0. Let's use the distance formula for both of these lines. Let's first use it for p, the blue line. The distance p is given as, you put in the value 0, 0. So x equals to 0 and y equals to 0. Both of these things vanish. What you're left with is minus k cos 2 theta, because in the standard form, this moves to the left hand side. So minus k cos 2 theta mod of this divided by root of cos square theta plus sin square theta. So that's the denominator. Let's do the same for this green line q. That's going to be equal to 0, 0. So these two vanish. We only have k. So that's minus k mod of this divided by square root of secant square theta plus cosecant square theta. So square root of a square plus b square. That's what we have. Now p is this. Let's simplify it. Cos square plus sin square is 1. Mod of negative number is the same as mod of the positive number. So p is mod of k cos 2 theta. And what's q? Let's convert secant and cosecant as sine and cos. We have mod of k divided by 1 by cos square theta plus 1 by sin square theta. Secant is 1 by cos, cosecant is 1 by sin. Alright, let's take the LCM. This becomes q equals to mod of k by square root of, the denominator is cos square theta sin square theta, and here we have sin square plus cos square. Okay, so sin square plus cos square is 1. This means it's the reciprocal of cos square theta sin square theta, square root of it. That's mod of sin theta cos theta. This goes in the numerator. So q is equals to k sin theta cos theta mod of all these three. So that's q, and this is p. Now we need p square plus 4q square equals to k square. This is what we have to prove. So let's start from the left hand side. Let's square p and let's square q. P square plus q square is k square cos square 2 theta plus k square sin square theta cos square theta. When we are squaring, we don't need the mod sign. This is p square plus q square. We need p square plus 4q square. So let's fix this. This plus 4 times this. And we can strategically place 4 next to sin square theta and cos square theta because we're aiming to eliminate theta. Here we have cos square 2 theta. If we somehow manage to have sin square 2 theta here, we can add them up to 1 and we can eliminate theta. Let's see how we can do that. P square plus 4q square, that's, this thing remains the same, k square cos square 2 theta. Here we can take 2 sin theta cos theta. This is the square of 2 sin theta cos theta. So k square times 2 sin theta cos theta square, this becomes sin 2 theta, which means what we have is k square cos square 2 theta plus k square sin square 2 theta. Now we can take k square common. This becomes cos square 2 theta plus sin square 2 theta. All of this adds up to 1. So what we end up with is p square plus 4q square equals to k square. And that's exactly what we have to prove. Let's solve a few more. Here's the next one. If p is the length of the perpendicular from the origin to the line whose intercepts on axes are a and b, then show that 1 by p square equals to 1 by a square plus 1 by b square. So let's break down what this question is saying. We have a line whose intercepts on the x and y axis are a and b. and P is given as the length of the perpendicular from the origin. So let's form the equation. We have the intercepts, so let's use the intercept form. Equation of a line in intercept form is x by a plus y by b equals to 1. Now the distance of origin from this line is given as p. Let's use that. Distance from origin is p, which means p equals to mod of, when you put 0 and 0, these two vanish, we have minus 1. So mod of minus 1 divided by square root of, here we have 1 by a square and 1 by b square. We're looking for p square, so let's square this. P square equals to 1 by, the root vanishes, we have 1 by a square plus 1 by b square. This denominator is exactly what we need. This is the right hand side. So let's keep it as is. Let's move this thing here. So p square comes to the bottom. 1 by a square plus 1 by b square is equal to 1 by p square. And our job is done here. This is exactly what we have to prove. Let's solve one final problem, a challenging one. Here's the problem. Prove that the product of the lengths of the perpendiculars drawn from the points root a square minus b square comma 0 and minus root a square minus b square comma 0 to the line x by a cos theta plus y by b sin theta equals to 1 is b square. We have to prove that from these 2 points, if we draw perpendiculars to this line and multiply the lengths, we get b square. So this needs a rigorous proof. Pause the video, try this on your own. Okay, let's do this together. Let's break this problem down. Let's start with this point and this point. So let's find the lengths. The length of the perpendicular from root a square minus b square comma 0 is given as this. So if you put x as root a square minus b square and y as 0, we get this. X root a square minus b square. Y is 0. Everything else remains the same. The denominator is square root of whatever is next to x, which is cos square by a square, and whatever is next to y, squaring this, sine square by b square. So that's the denominator. This is the numerator. The same thing works here. Here point x is minus root a square minus b square. So wherever we have plus, we have put minus. Most of it remains the same. Okay, we can simplify this. This is 0. So this is root of a square minus b square by a cos theta minus 1 mod of this divided by the denominator. And this is the same thing because it's minus and minus. We can take the minus sign out. We can say that this plus 1 is our numerator. Because we have mod, we can get rid of the negative sign. So this looks very similar. Here we have something minus 1. Here we have something plus 1. All right. What's the next step? What are we asked? We're asked to prove that the product of lengths of these perpendiculars is something, is b square. So now we need to multiply these two. So let's do that. The denominator is square root of something. The denominator is same. So when we multiply, the root vanishes. We have cos square theta by a square plus sine square theta by b square. In the numerator, we have mod of something minus 1 times mod of something plus 1. That same thing plus 1. So here we have x minus y times x plus y. This is x square minus y square. So we can do that. We can square this. This is a square minus b square by a square cos square theta minus 1 square is 1. So this is the numerator, mod of this, divided by the denominator is b square cos square plus a square sine square divided by a square b square. All right. It still looks a little messy. We need this to be b square, which means theta will get eliminated somehow. In fact, a will also get eliminated somehow. So let's keep going. We have a square by a square, that's 1, and b square by a square. So this is, if we split it, this is 1 minus b square by a square. Let's multiply this with cos square. So we have cos square theta times a square by a square, that's 1. So we have cos square theta minus b square by a square cos square theta. And because we want to eliminate theta, this 1 can be broken down as sine square theta plus cos square theta. Minus 1 means we have minus sine square theta minus cos square theta. So here we can cancel cos square theta. In the numerator, we have minus this, mod of it, which means we can get rid of the negative sign. We have b square by a square cos square theta plus sine square theta, mod of this, divided by b square cos square theta plus a square sine square theta divided by a square b square. All right. Now numerator and denominator looking similar. We can take the LCM. We have b square cos square theta plus a square sine square theta divided by a square. That's the numerator. And denominator is b square cos square theta plus a square sine square theta by a square b square. all of these are squares and we're adding things, which means we can get rid of the mod. So the numerator has b square cos square theta plus a square sin square theta. We have the same thing in the denominator. So we can cancel this out. So theta goes away. We have 1 by a square divided by 1 by a square b square. Now a square is in the denominator, a square is in the denominator. So we can cancel this out and a also goes away. We have 1 by 1 in the numerator, that's 1, and 1 by b square in the denominator. So this is 1 divided by 1 by b square, and drum roll, this becomes b square, which is exactly what we have to prove.